All right. So I've already kind of mentioned this in 5.5 because it's hard not to complete the story, but a redox reaction is spontaneous if it can occur without any added energy. If you're going to use the standard reduction potential table to predict reactions, it's when you combine two half reactions together. The species that's higher on the table has a more positive electron potential or electrical potential, and it is more likely to be reduced and act as the oxidizing agent, whereas the species that are lower on the table have a more negative electric potential, and so they are more likely to be oxidized or act as the reducing agent. To calculate the cell potential, so when we put two half reactions together, it's always the sum of the reduction potential and the oxidation potential gives you the cell potential. And then to interpret this cell potential, if it is greater than 0, the reaction will be spontaneous. If it's less than 0, it is not spontaneous. You would have to apply a voltage to make it to occur. And if it was 0, then it's at equilibrium. Now, only one direction will be spontaneous, and that'll make more sense as we do some. So let's look at the combination of zinc and copper. Now, I've already taken these off the table, and I found the two reduction half reactions. So copper 2 plus 2 electrons will be reduced to form copper solid, and zinc 2 plus 2 electrons will reduce to become zinc solid. But these have equilibrium arrows. What we want to figure out is which of these half reactions is going to act as the oxidizing agent and which one is going to act as the reducing agent. In other words, which one's going to be reduced and which one's going to be oxidized. Because the copper 2 plus has a more positive potential, it is higher on the table, it is the one that is going to be reduced. So we're going to write the copper 2 plus reaction as the reduction reaction, and we're going to write the zinc as the oxidation, and we're going to reverse its potential. So then the overall redox reaction, you're going to cut out the electrons, and you're going to say that copper ions and zinc form copper solid and zinc ions. And I didn't include the states here. I was kind of copying this from the textbook, and they don't include states, but if we wanted to be perfect, we would. But the overall cell potential is positive 0.110, and this is a spontaneous reaction. Now, so two reasons this is spontaneous. One is because we made it spontaneous. We picked the copper 2 plus to be the reduction reaction because it was higher on the table. And so we kind of forced our E value to come out as positive. So we don't always write the E value, but just know if you always pick the species to be reduced that's higher on the table, you will always get a spontaneous reaction. So let's just look at that for a second. So let's look at the different combinations of lead and magnesium. Let's split my screen again. Okay, so when we look at the oxidation and reduction of lead and magnesium, this is said specifically, I want to use the reactants of lead and magnesium solid. So I'm going to use magnesium and I'm going to use lead. Now this one's set up to succeed. I have the lead ion higher on the table than the magnesium ion or magnesium metal. So the lead ion is going to be my reduction reaction. Pb2 plus 2 electrons goes to, I'm writing a half reaction, so I'm going to switch to a one-way arrow, to Pb solid. And the E, I'll just shrink this down again. The E value of this reaction is negative 0.13, and that's okay. It's still going to be a spontaneous reaction because then I'm going to use magnesium. Now magnesium as an oxidation, so magnesium solid as an oxidation is going to form magnesium ions and 2 electrons, and it has a potential or an oxidation potential of positive 2.37. So even though this lead ion reaction or reduction had a negative potential, the magnesium has such a strength as being a reducing agent. It has such a tendency to be oxidized that it sort of overrides it in a way. And my overall potential is 2.37 plus negative 0.13, which gives me an overall potential of 2.24, which means that this is a spontaneous reaction. And again, the overall reaction, just don't include the electrons, is lead ions plus magnesium metal forms. Now, when you go to your overall reaction, you go back to a two-way arrow. And this is going to form lead solid and magnesium ions. Oops, didn't include the plus. Awesome. In the next reaction, we're going to choose the opposites as our reactants. We're going to choose the lead solid and the magnesium ion. So let's go over here, just erase what I've got on here, because this time we're going to start with the lead and the magnesium ion. I lost magnesium. There it is. Okay, so this time I'm saying that my lead has to be my oxidation reaction. So I'm going to put my lead as Pb solid forms Pb2 plus 2 electrons. And then my reduction is going to be my magnesium 2 plus 2 electrons forms my magnesium solid. Now, when we look at the potentials of these, so the potential of magnesium being reduced is negative 0.237, and the potential of the lead to be oxidized is actually positive. It's more likely than it being reduced. But because it's with such a strong reducing agent, it's actually not going to happen. So we would do negative 0.237 plus the 0.13 comes out as an overall negative potential, which means that this is unlikely to happen. The other thing I want to point out at this point here is that the reaction of lead ions and magnesium metal had an overall potential of positive 2.24, and then the reverse has a potential of negative 2.24. We're going to go over that again, but it's good to know that now, is that only one of the directions will be spontaneous. So only the lead ions and the magnesium solid would be the spontaneous reaction. The reverse of that, which is the lead metal and the magnesium ions, would be non-spontaneous. And then lastly, the overall reaction here is the magnesium ions and the lead solid. And again, we use an equilibrium now because it's showing that these, like this reaction and this reaction, can occur either way, even though there's more of a tendency for it to occur one way. We go back to equilibrium. We'll form magnesium solid and lead ions. Oh man, that's sync. Okay, and then the last thing here is just an impossible reaction. So both of these reactions up here, I used lead ions and magnesium solid, or lead solid and magnesium ions. But if I'd put the two metals together, or if I'd put the two ions together, it's an impossible reaction because I'd have two oxidizing agents or two reducing agents. So for example, if you looked at lead and magnesium, right, they're both oxidized. So it's never going to happen. Even if the E comes out as positive, it just can't happen. And same thing if I started with the ions, the oxidation reactions can't happen because you can't oxidize two things. Like there has to be something that wants the electrons and something that wants to give the electrons. That's the only way that reactions can occur. Okay, so I've got a list here of 4 different pairs of reactants, and we want to determine if the reaction is spontaneous or if no spontaneous reaction would occur. So I argue, I mean, this is the way the textbook wrote it. I argue there is 3 scenarios. There's spontaneous, non-spontaneous, and not possible, but they've just said, hey, spontaneous or not. Okay, so it's almost like no reaction. It's just not spontaneous. Okay, so we're looking to see if they're on opposite sides of the table. So let's just take off these little circles. Okay, so we've got chlorine gas, which I'm guessing is going to be somewhere near the top. Oh, there it is, way up there. Whoa, what did I just do? What did I just do? 1 second. I don't know how I did that. Okay, anyway, the chlorine gas is way up here. Okay, so that's going to act as a reactant, and then we've got the bromide. So they're not going to choose something that can be oxidized and reduced. They'll always choose something that can only be one or the other. So when you're looking on both sides of the reaction. So then I'm looking for my bromide ion, and it's down here. Now, again, my reduction reaction is higher than my oxidation reaction, which to me right away says that this is going to be spontaneous. If spontaneous, we have to write out the complete reaction. So it's going to be chlorine forms, chlorine plus 2 electrons. forms 2 chloride ions, and then 2 bromides forms bromide liquid and 2 electrons. And so my overall reaction, and sometimes they'll just ask you for the products, but you've got chloride plus 2 bromide ions, equilibrium arrow is going to form 2 chloride ions and bromide liquid. If I wanted to double check that this is spontaneous, I can add their E's together. So the chloride is positive 1.36. And then the oxidation of the bromide ion is going to be negative 1.09. So it would rather be reduced, but it gets overridden by a stronger oxidizing agent. And we get an overall of positive 0.27 volts. So that reaffirms that this is spontaneous. Okay, let's look for nickel and lead. So nickel ions is down here at negative 0.26, and then the lead is right above it here. So this time I have my lead is higher than my nickel. So right away I'm going to say this is not spontaneous. Non-spontaneous. It doesn't mean a reaction won't occur, but it means that it won't occur spontaneously. You would have to apply a voltage to make it happen. So according to the textbook, we would say no reaction. According to chemistry, just be careful. It's non-spontaneous, which is why no reaction will spontaneously occur. Okay, so what about calcium and strontium? Calcium I'm going to guess is down here. So this is my calcium ion, and then strontium is right below it. Since my calcium is higher than my strontium, this is going to be a spontaneous reaction. So the calcium 2 plus 2 electrons is going to form calcium solid, and then my strontium solid is going to form strontium 2 plus and 2 electrons. My overall reaction will be calcium plus strontium forms calcium and strontium ions. My overall potential, so the calcium is negative 0.287, but then my strontium is going to be positive 0.28 or 2.89. Which means it's not very likely to happen. They're way too close together. But it's 0.02 volts. And then the last one, strontium 2 plus and calcium solid. So we've got, let's just erase that. This time we've got strontium 2 plus and the calcium solid. This is the reverse of the reaction we just did. It has my oxidation higher than my reduction, which means it's never going to happen. This would be non-spontaneous. So it's going to be no spontaneous reaction, and its E value would be negative 0.02 volts, right? The opposite of this one. Okay, last little question to ask you this in a different way. Which of the following substances will oxidize iron 2 plus? So if we find iron 2 plus on my table, there it is there. Which of the following, never mind, because it says will oxidize. That is iron 2 plus being reduced. So what we have to look for is iron 2 plus being oxidized. So that must be on the right-hand side, way up here. Okay, so this is iron 2 plus. What will cause this reaction to be reduced, to be oxidized, would have to be something higher. So we're going to look for one of these as a reactant on the left-hand side. So let's start near the top and see if we can find any of them. So what am I looking for? MnO4 in an acidic solution is this one. This is higher, so this one is the only one of this group that will oxidize Fe2+. Now to prove that to you, I'd have to find the rest of them. I don't really want to. But chloride is on the same side, so definitely not. Water's on the same side, so definitely not. And then the sodium ion is way down here. So definitely not. This guy definitely wants to be oxidized itself. Okay, and then the reverse of that, it says which of the following will reduce Fe2 plus. So you need to switch to that Fe2 plus I originally circled, so this one, and we want to know which of the following will reduce. So we're looking for a reducing agent on the right hand side that is lower. So my choices are chlorine gas, that's not down here. Copper 2 plus, that's not down here. Sodium, that's my guess. It is my metal. And then last little kind of theory question, which substance can be reduced by tin, but not by tin 4 plus? So which can be reduced by? That means that I'm looking for an oxidizing, I'm looking for tin and tin 4 plus acting as an oxidizing agent. So I'm looking, or reducing agent, sorry. I shouldn't be making all these these videos in one night. I'm starting to go loopy. Okay, so we're going to look for tin and tin 4 plus as what? I'm looking for a substance that can be reduced. So I'm looking for them being oxidized. So there is tin. And then tin 4 plus is where? I see tin 2 plus. Where is tin 4 plus? So I'm looking for which substance can be reduced by tin, but not by tin 4 plus. Are you guys seeing it? Or did I just make a typo? I think I meant to put tin 2 plus. Which of the following can be reduced by tin, but not tin 4 plus? I said to double check. That's totally a typo. So this should be 2. Okay. So which of the following can be reduced by tin, but not by tin 2 plus? So I'm looking for something that's higher on the table than tin, but lower than tin 2 plus. So my answers are going to be all of these guys. So it's going to be that S solid, but acidic. Right? So it has to be an acidic situation. The 2 hydrogens, which I don't need to put the 2. I can just put hydrogen. And the lead 2 plus. So all of these substances will be reduced when it's in the presence of tin solid, but it will not be reduced by tin 2 plus. Sorry about the typo. Okay, hopefully that makes you feel confident going to do your homework, and then come back and we'll do the next lesson.